Okay, we are in section 15.2, and so I'm going to finish the notes in this recording, post the notes, and then instead of finishing the notes on Monday, we're going to practice some of these problems. So we have double integrals. Some of these problems are easier than others. A trick we learned was Fubini's theorem, which tells us that we can integrate in any order we want. So even if it's written to do the integral with respect to y first, we can switch it and do it with in terms of x first and then y. And we can do that, we'll get the same answer either way. So we barely started this example here, example 2, that we're given this general double integral notation, and then we get to decide what order we're going to integrate in. So we notice that when we have the integration with respect to y, that would not be wise to do first because we have a function of y times a function of y in the sign of xy. So in terms of integration, that's not a good sign. That's going to involve some sort of special technique. What it would involve is by parts, which I told you I'd try to avoid giving you any problems that you had to integrate by parts. So big clue there that that's not going to be the best way to do it. Notice there's only one x in here, which holding y fixed and doing the integral with respect to x first would probably be easier, just based on that. So it turns out it is easier, but because we got a composite function here, it's sine of x, y, and not just sine of x, for example, then it turns out we have to use a substitution technique. And so we have to use a substitution technique with like a partial integral, which is called the iterated integral. And so that's kind of like a big step up right from the beginning here if you're having trouble even remembering what the substitution rule is. So we're actually going to do a couple problems that when section 5.5 is covered are kind of considered on the easier type. I don't think we're going to have to do some of the more advanced ones, but we're going to review that first because you're going to be really have no idea if you don't have that down. So here we go. We will come back to this example, but going back to our Calc 1 situation with a single integral, the substitution rule comes into play when we have a composite function is one clue, and then potentially we have times a function that's in terms of x. If it happens to be the derivative of the inner function, that's really good news because then that means that you can use the substitution rule. And the substitution rule kind of undoes the chain rule. You can kind of think of it as being performing that kind of thing. There's some little bit of notation difference, but it's pretty much what it is. So the way we do this is we let g of x equal u, and then what that allows us to do is to rewrite the integral in terms of u. It'll be simpler because u is the inner function of the composite function. And then if you can do that integral totally in terms of u, then you've accomplished your goal of evaluating the integral. And then you just substitute back the g of x for u. So that's the general idea. And let's look at a specific example. So here we have the integral of 2x times the root of 1 plus x squared. Now it's tempting to try to simplify this and take the root of each of these terms separately, 1 and x squared, but you're not allowed to do that. That algebra is just not legit. So we are stuck with that square root, and it's a composite function. Now you could like put the 2x squared and square root and put it together, but it turns out that's not helpful either. So you're kind of stuck with this form. This actually is a pretty easy problem as far as integration by substitution goes. So notice, first of all, it is a composite function here. The inside of the composite function will be your u, or your g of x. We're going to call them by the same thing, or have like two different names for the same thing, depending on the context here. So my g of x, or inner function, just like in the chain rule, is 1 plus x squared. So now, the next thing you need to do is take the derivative of that as just some side work and see what you get. We have 2x. That's really good news because if you look at the form of the substitution rule, What this is saying is like you have this f of g of x function where g of x is going to be let to be equal to u, and then if you have that g prime x, dx is always there, and you can identify that part, you turn that into du, and then you got an integral in terms of u. So because the 2x is hanging out here times the composite function, we always have the dx hanging out, then we're going to be able to use this substitution rule. So the way that you do this next part varies. The way I choose to do it is I, at least initially to kind of show this notation, how this works out, that our g of x is u. So if you're talking about the derivative of g of x, you can use this notation here with the Newton notation. Or if you use u for g, you can write it in Leibniz as du over dx. The reason I want to do that is because I'm trying to find or write the integral in terms of u. So du is equal to g prime of x dx if I separate the Leibniz notation into like differentials. So there it is. Du is equal to 2x dx. So if I can do that substitution, that's perfect, and that's exactly what I have. I can rearrange the multiplication and have 2x dx, and then I will have the square root of u. So here's just doing the work ahead of time to say, okay, do I have all my things accounted for? Am I able to use this technique at all? If I am, I'm able to rewrite this integral totally in terms of u, and then you also have to account for the du, which is accounted for because the du, by my choice of u, has to be 2x dx, and it's there. So all that work to get this integral of the square root of u, du. That's the easy integral. It's just u to the 1/2. I do the integration with respect to u. Use that power rule thing. I have the 3/2 as my new power divided by that thing. Then, because it's the indefinite integral, I just put the plus c. Then, simplifying 1 over 3/2 multiplied by the reciprocal, 1 times 2/3, 2/3. My u was 1 plus x squared in the beginning. I just plug that back in here, and I'm done. So that's it. That is how you do the substitution technique. Let's look at the next one here. So notice we got a composite function here. Notice that there's not algebra here that I can do to make this simpler, and I have a function of x divided by another function of x that's a composite function. So it's kind of complicated. This is not something that can just be simplified into like x to the 3/2 or something that I can use just integrate term by term or something like that. So I'm looking to use the substitution technique, and my first step there is to identify the composite function. So the composite function here, at least part of that, is the square root of 1 minus 4x squared in the denominator here. So that is definitely a composite function down there, and your u, or g of x, would be 1 minus 4x squared. So just go with that. You identify the u and the g of x, they're the same thing here. Then take the derivative of that, you get negative 8x. And then I did the algebra up here, but once you get good at this, you don't have to do the algebra. What that means is that du is equal to negative 8x dx. Sometimes the negative 8x dx is there, sometimes it's not. Of course the dx is always there. So I check and I see that yes, I can write this as, scrolling up here, the composite function f of g of x times g prime of x dx. So that means that this technique will work. So this part here is the du, and then underneath here I'm going to have square root of u. This is the substitution in terms of u, and I have du over the square root of u, which notice you can just use the power rule for that if you just do a bit of algebra. So this is going to be 1 over u to the 1/2, which can be written as u to the negative 1/2 overall. Just use the power rule, and you get plus 1 is 1/2 power, divide by that, put your plus c, back substitute your u in there, and you're done. You get 2 times the root of 1 minus 4x squared. Okay, last example. So those were both like really canned, basically, where you're just going to do the substitution rule. It's all set up for you. So often, again, I'm not going to try to give you the hard ones, but often they're going to be not exactly everything's good to go, but they're just going to be a difference of a constant, and you can account for that. So like this one, for example, it would be nice if I could just bring the 9 in, but because it's a minus here, I can't do that. That algebra is not allowed. And you can think of this, the reason why there is, if I had that thing in parentheses and it was multiplied out and I had 9 of them, that's what this means. You would have to FOIL all that out, and you would have all these terms and stuff. It wouldn't just simply be 1 to the 9th minus 2x, that quantity, to the 9th. That's not what it would be. So they're not equivalent. Anyway, it's a composite function. So potentially substitution would be useful. So the u, or g of x, is the inside of the composite function, which is 1 minus 2x. So you take the derivative of that and you get negative 2. And so the ones that we've done so far, that negative 2 would just be hanging out there, and it'd be times the composite function, and the dx is there. Well, this time, of course, we always have the dx, but we do not have times negative 2. Now, if the thing you're looking for is just a constant, and it's not a variable thing, like for example, this doesn't say negative 2x. Like if there's no x there, unless there's some magic algebra or some other things when these get harder, then you can't fix it. I mean, then this technique falls apart and you can't do it. But if you just have a constant here that's not there, then that's an easy fix. So, looking at this, what we'd have so far is u to the 9th. Now handling the du part, there's no negative 2 is what we were saying. Well, the way that you can get a negative 2, one way to do this is you take this little equation for du that you had, divide by negative 2 on both sides, and note that you get a little substitution for dx, that is negative du over 2. So you can do that for dx, and then what you'll have is u to the 9th times negative du over 2. And notice that that is an integral that is actually all in terms of u, so that's allowed, and we can do it, and that constant's not screwing things up too much. I can even take out the negative 1/2 if I want to. So now what I have is negative 1/2 times the integral of u to the 9th with respect to u. So I do that integration just using the power rule. I got the times negative 1/2 hanging out, constant multiple rule. And I'll have the 1/10 times u to the 10th plus c, simplify, put your u back in terms of x, and you're done. So going back now to example 2, with that background in mind, we said the integral in terms of x would be easier. Now with our substitution eyes on, notice that we have a composite function, sine of x times y. It's not just sine of x. So it's a composite function. When we fix y, we can treat that as like a constant on the inside and the out. We know that the integral of sine is negative cosine. To kind of get used to this fixing y and doing all this, ask yourself, what would be the integral of 2 sine of 2x? Well, again with substitution eyes on, we still got a composite function, 2x, that's your u is equal to 2x, and then you'd find the derivative of that and get 2, and you can make the little differential equation du is equal to 2 dx. So is the 2 hanging out there? Absolutely. So that makes it easy in substitution land. So our du is 2 dx, and then we can account for the composite function as sine u. we know how to find the integral of sine u with respect to u. It's negative cosine u, plug in u equals 2x. So that was, we keep on going to background, and now we're actually ready to do this integral in this section. So anyway, here we go. For real. So the y is fixed. It's like the 2 up here. And so with substitution i's on, our g of x is u is xy, taking the derivative of that, and this is not legit notation, but we're just going to go with it. When I do the derivative of xy with respect to x, I get y. So it's a partial, for real. But then when we write it as a differential, it's du is equal to y dx. Do we have y dx hanging out? Yes, we do. That's really good news. Then I can just write this as sine of u du. So we just did the substitution. Now, I didn't go over the Calc 1 scenario with the limits of integration written in. But this is the notation here. Try not to get too bogged down on it. But because I'm changing the integral in terms of u, the limits of integration are no longer in terms of x. They need to be in terms of u for everything to be consistent. So u is equal to g of x, so that's why I wrote g of 1 and g of 2. You could actually find those. There's two ways to do the definite integrals with substitution. I'm always going to go back in terms of x just to have one thing that I'm always doing, but realize that you have that as an option. So this is a legit notation. If you kind of forget that, I'm not going to hold it against you, I don't think. Or I'll just say I won't. And I won't. But I need to show you the legit notation here. Okay, let's move on. The integral of sine u with respect to u is negative cosine u. Then what I'm going to do, just like from above, I'm going to plug back in terms of x, and now I can take off that g part because everything's in terms of, like back in terms of x there for that part. Oh, okay, so now, remember that this integral is in terms of x. So we're going to plug in x equals 2 and do the fundamental theorem of calculus part 2. So we have cosine of x being replaced by 2. I pulled my negative out, so that's where that is, minus cosine of 1 times y. Now, I'm going to try to look at doing the integral with respect to y pretty soon. So something to notice is that because now I have a function of y minus a function of y, that it would be smart to split up this integral on the minus sign, and that's a legit move. So I'm going to do this integral in two integrals. So looking at just this first integral, I distributed, or did I forget to distribute my negative? I think I did. If I mark that, all my boxes are going to get messed up. So I'll fix this, but it looks like I forgot to distribute my negative. So if I distribute this, it's going to be plus right here. Okay, so anyway, looking at the first integral, notice it's a composite function. So you do need to do substitution. Once you get good at this, you don't actually show the steps, but we're starting out, so I'm going to show all the steps. So my u is equal to 2y. That means my derivative of 2y is 2, and my du is equal to 2 dy. There's no 2 hanging out. So I do the bit of algebra, and for dy I'm going to plug in du over 2. So doing that step, I'll show you that first. Finish that thought. Then we're going to have our cosine of u times du over 2. And then I can pull out, ooh, I forgot to do my 2 as well. Okay, I'm just going to have to get rid of my boxes or deal with the fact that those are not going to be there. Got too many mistakes here. So this was plus, and then what else happened here? I forgot my 1/2. Okay, there we go. There we go. So then what we got here, the integral of cosine of u is going to be sine u, but there's this negative up front. Here's my notation saying, okay, I got to go back in terms of what I got. I have this in u and I want to put it in terms of x eventually. So, or excuse me, y, because we're doing this with y. So the 2y comes back, and then I can strip off the g stuff there, and I have 0 and pi there. So then we'll plug it back in a second. Now going all the way back to this integral of cosine y with respect to y, that's just going to be sine y for its integral, no substitution allowed, or not allowed, but needed. Then we plug in, could have done that back there, and we're going to have to plug in here as well. What happened? Missed some stuff here. 2y plus oh, I see what happened. So we need the 2 here. Need to carry that negative. And then it should have been sine of pi is 0. Sine of 0 is 0. So then what was missing here was a plus 0 and then an equal sign. Alright, sorry about that. Okay, now moving on to the next step. Plugging in pi, plugging in 0, and then this is all over 2. So if we do this calculation here, well, sine of 2 pi is also 0, sine of 0 is also 0. So that was kind of a lot of work to get 0, but there it is. It's just 0, and that's why I didn't, you know, that 2, I didn't notice that mistake. We just end up getting 0. So that was hard fought, but hopefully you picked up this, you got a couple that you have to use substitution with this double integral. And you'll get some practice on Monday as well with another example. Alright, one more trick. So if you have an integral, double integral here, and it just ends up being the product of a function in x and a function of y, and it's, you don't have a part that is in terms of x and y and it can't be pulled apart, then there's this cool trick where you can basically just take the integral of each separately with their respective type or their respective variable and multiply it afterwards. So that's a pretty cool trick, and we can use it on this example right here. We have x squared y. Notice that we could write those distinctly as a factor of a function of x times, you know, another one that's in terms of y. So we're going to use that trick. Okay, order doesn't matter. I'm just going to do the x stuff first. So the 0 and the 3 are having to do with the x. And then I'm going to multiply by the integral of y with respect to y, is what that handy rule says we can do. So this is just 2 Calc 1 integrals. Figure them out. I get 1/3 times x cubed, and we still have to evaluate that. And then the other one, in terms of y, is going to be 1/2 y squared with its stuff that we're going to plug in. So we're going to get 1/3, I'm going to leave that out, and then we're going to have 3 to the 3rd minus 0. And that's going to be times 1/2. and then I'm going to have 2 squared minus 1 squared. So we'll work this out. We get 1/3 times 3 to the third times 1/2 times 4 minus 1 is 3. So we're going to have 27 halves. Just check that answer. Looks good. All right, one more example. Find the volume of the solid bounded by z equals 16 minus x squared, the planes y equals 0, y equals 5, x equals 0, and x equals 4. So, first of all, when we've looked at all these pictures of the volume of these solids created by having some sort of surface, they were above the xy plane. So, you know, we didn't do anything other than that, so you can kind of assume that, but just to convince ourselves we don't have any places where the surface is dipping below the xy plane. For this particular region we're talking about, notice that when you plug in the values of x here between 0 and 4, that the z is always going to be positive. Actually, it doesn't depend on y at all, so it's good in that respect. So this will be that situation where we have the surface above the xy plane, and so then when we find the area below that, bounded by all these different xy planes, that's going to be a positive volume, and there's not going to be like some negative thing going underneath the xy plane. So everything's good to go. We're going to do double integral of that z function, putting in the values for the integration, limits of integration, matching up the y's, have to go with the y's, and the x with the x. So the order of this one doesn't matter so much, so I just decided to do y first. And so remember, we're not doing derivatives, we're doing integrals, so a constant, I can do this integral to each term separately, by the way. I didn't actually write it that way, but that's what I was doing. So the constant 16, when you do the integral with respect to y, you got to attach a y there. And then if you have the minus x squared, we're holding it fixed, so it's like a constant, and we get the same type of thing there, where it's just going to be attached to a times y there. Then you got to plug in with the 0 and the 5 goes first, minus the 0, which this one ends up being 0. So we end up with 80 minus 5x squared. This integral that results will just be a Calc 1 integral. So you just do that as usual, and then plug and chug. So if you do that correctly, you get 640 over 3. So like I said, that's it for the notes. I wanted you to go through this because it is probably been a while since a lot of you have done integration. And in exchange, on Monday we'll do more examples, but you'll actually work them out. And then we'll have a little bit of time to move on into 15.3. That's it.